In this video, we are going to first set up the architectural plan, and then I will show you how to convert that to the structural drawing for precast concrete. In this video, we are going to start out drawing our architectural plan, and then we will convert that to our structural plan for our precast building. The first thing we need to do is go to New, and we're going to go to Architectural, and we want to go to Commercial, and we want to say Open, and we're going to say OK. We're going to start out by setting up our grid system just like we've done in the past. So I'm going to click up here under Architecture on Grid, and I'm going to start over here to the left, and I'm going to go up, and I'm going to put in 5 grid lines. I want to space them 50 feet apart. I need to move my elevation marker outside of that area. Now I'm going to do my horizontal grids, and I'm going to have 7 grids. So again, I go back to my architecture and I go to grid, and I'm going to start up here on the right side and bring it over here. And the very first thing I need to do is I need to change this to the letter A. Then I'm going to go ahead and create the next one, and it is only going to be 5 feet from this one. So I could either pick it exactly so I don't have to go back and change it, or I could just do it and then put it in. The rest of my grids are going to be 30 feet apart, and I want to go down till I get to the letter G, and I want to space them 30 feet apart. And I'm going to go ahead and extend my other grid lines down because again I want them to come past where my building is going to be. And again, I need to move my elevation markers. I want to kind of put everything in the middle. So I should be set. The next thing is I want to go to my elevations, and it doesn't matter which one I go to. For now, I'm just going to leave my top of footing and my bottom of footing. My level 1 is going to be at 0, and then I want to set my roof at 20 feet. I'm going to add my level 2 by again going to my architecture tab, grabbing my level line, starting over here to the left, kind of just sticking it in between until it aligns. And that one I want to be at 10 feet. Again, I need to bring these out to my column lines, and really my column lines need to probably be a little bit higher. So I'm going to grab one of them and pull this up a little bit so that I have adequate overlap. And then I always go back and I check my east to make sure it is correct. Again, I need to drag these out. I need to drag these up and these down. Over here, I'm good. Now I'm going to go to my south elevation. I need to drag these out a little bit because again I want adequate room beyond my building. And same with my west elevation. Everything looks good now. I'm going to go back to my level 1 plan, and we're ready to start drawing. So the first thing I want to do is I want to create my wall types. But before we do that, I want to talk about precast wall construction. The type of wall that we are going to create for our perimeter walls is a concrete insulated wall panel. Precast concrete insulated sandwich wall panels have gained popularity over the years. The reasons for their increased use in place of more traditional materials include speed of erection. It can be done very, very quickly. Cold weather doesn't come into play, and it's shipped to the site as needed. The design flexibility. You can have a lot of finishes and patterns, including inset brick, stone, and abrasive blasting. The thermal efficiency. Edge to edge, top to bottom, rigid insulation can be used within a relatively thin wall, providing a high effective R value. The thermal mass of the concrete provides an added benefit by slowing heat transmission through the wall, flattening out the temperature swings. It can be used in conjunction with the building's thermal performance, can actually double using precast wall elements. This in turn can reduce the size of HVAC units needed. And cost-wise, it can be competitive. Precast concrete wall panels can be cost-effective alternative to masonry or other hard wall systems, as they do not require as much labor as other systems. A typical insulated panel has two outer concrete layers, or what they call withes, separated by rigid insulation, and is cast in a long line form in a plant. One or both of the withes are usually pre-stressed to reduce cracking and improve performance. Panels can carry roof and floor loads or just act as cladding, load-bearing versus non-load-bearing. There are many different types of panel designs. There are non-composite, which is a non-composite panel. The concrete withes act independently. This design is typically used when a high insulation value is required, such as for a cooler or freezer building. The withes are isolated by high-performance rigid insulation and are connected together solely by the thermally non-conductive pin connectors. The pins are made of either a fiberglass or vinyl ester or polypropylene plastic or other non-conductive material. The interior structural withe is usually much thicker than the exterior face withe. Fully composite panels, the withes act together as a unit for horizontal and shear transfer. A typical composite panel is 8 times stiffer, can take 3 times the stress without cracking, and has twice the ultimate strength of a non-composite panel or similar thickness. Composite panels are typically less expensive than non-composite panels, primarily because they can carry more load and can be made taller and thinner. The inside and outside withes are usually stressed with pre-stressing strand and made of equal thicknesses in order to minimize internal strains. Sometimes the panel is made solid below the floor line and above the parapet outside the building envelope to help with composite action. Unlike non-composite panels, composite panels often bow outward when exposed to direct sunlight due to the temperature increase and subsequent expansion of the outer withe. The characteristic is normal but should be taken into account if panels are attached to or abut against an intermediate floor mid-height. Then we have partially composite. Partially composite panels provide less than full shear transfer between withes. They behave in a manner in between composite and non-composite. The degree of composite action is determined by load tests performed by an independent testing lab. Proprietary partially composite wall systems are now available, which combine the high insulating value of non-composite panels with the strength and slenderness of composite panels. This is accomplished by using non-conductive truss grid or individual connectors between the withes for shear transfer. Partial composite action provides sufficient strength for most application. It is important to keep the distinctions between panel types in mind when determining a standard wall thickness for a project. Since the panels are cast in a form that is usually several hundred feet long, the thickness should ideally be the same for all the panels on a particular project to avoid excessive setup costs. Occasionally, a designer will select a panel thickness based on the assumption of full composite action, but then insist on thermal performance that can only be achieved with a thicker, more expensive non-composite design. Working with a local precast manufacturer to estimate a panel thickness can ensure design requirements are met with the most economical panel. There are also dimensional considerations that you have to take into account. For pre-stressed panels, the panel width is limited to the precaster's long line form width, as well as shipping restrictions. Panels more than 12 feet wide may require special handling, and panels wider than 14 feet can be a challenge to ship by road due to the lane width and minimum bridge height along the chosen route. Individual panels are more flexible with possible lengths of 70 feet or more. Standard flatbed trucks can carry panels up to 40 feet long with a total cargo weight limit of 40,000 pounds. For example, a standard truck could carry 2 panels with a unit weight of 75 pounds per square foot and dimensions of 8 foot wide by up to 33 feet long each. There is a major cost advantage to being able to ship 2 panels in one load if feasible. There are many other elements that you have to take into consideration when using precast. You have to look at manufacturing tolerances, design responsibility, structural planning, handling loads, brace design, connection design, etc. That's a lot of information, but again, it's important to understand the differences in the types of panels that are available and all of the other elements that go into precast panels. We are going to keep our wall pretty simple. In the next video, we will start constructing our precast walls and continuing with our architectural plan.